Friends, welcome back to my channel. So today we're going to look at another interview question, and before we get into that, I just want to request you to subscribe to my channel if you haven't done it already. Okay, now let's jump into the question. The question that we're looking at today is: write a Python program to check whether a number is prime or not. So if you can remember your school days mathematics, a prime number is only divisible by itself and the number 1, and it's not divisible by any other number. So I have a couple of solutions for this problem, right? So first one, let's take a look at the solution 1, which is the normal method, the method that most people come up with um, at first, but it's not necessarily efficient. So in this method, what I have is I have a counter. So this counter is not really required for the solution. So we have another variable, a Boolean variable, and we have a few ifs and a for loop, right? So and this one is if the number is less than 2, we know that 0 and 1 are not prime, so we actually just do that right away. If the number is equal to 2, we know that that's an even prime number, and that's the only even prime number, and we print that right away. If it's greater than 2, then we actually we iterate over this range of numbers, the range being 2 through, let's say if the number that was uh, passed in as the parameter was 17, then we would have the range 2 through 16, because in the range function, this number that we specify in the second position is not included, it's excluded. So 2 through 16, and if none of these numbers, if we take each number and then if we do 17 by 2 in the first iteration, and that's not divisible, and 17 by 3, 17 by 4, 17 by 5, and so on, and then we run out of the numbers in this list, then we exit the for loop, at which point we know that this number is only divisible by the number itself and 1, and not by any other number, because we ran a for loop for the other numbers, and then we were out of this for loop at this point, and now we have just a just to check whether this boolean variable is still true, because if this number was indeed divisible in the for loop, we set it to false. So this is kind of like a straightforward solution, but it's not an efficient solution. So then I implemented this counter to kind of like show the performance of this for loop, right? So I just want to see, like, ignore these other statements outside the for loop, like, because this for loop is the main part that will consume most of the time and resources on the host it is running on, right? So I just want to see how many times this counter gets executed, right? So now we have, so I'm actually just calling that function and passing in this input 97 as parameter, and I want to check if 97 is a prime number. Yes, 97 is a prime number, I know that, but I just want to see if my program works. So I'm going to run it, and then it ran and it says 97 is prime, the number of iterations is 95. So it takes like as many iterations as the number that I pass in. uh, this is the worst case scenario, but yeah, but we want to always look at the performance of the worst case scenario, right? So 97 is prime, but it took 95 iterations of this for loop to make sure this is prime number, right? So obviously, like if you write this solution, the solution number one, uh, in your interview, then definitely you'll be asked to come up with a better solution. So before we write the program for it or write the algorithm for it, let's actually look at a few things to understand how we can improve the performance. So we saw what a prime number was. We know that a prime number is only divisible by that number itself and 1. And we also know or heard of composite numbers. A composite number is basically the opposite of prime numbers. It's not a prime number. So it has many factors apart from that number. Like, for example, 36 is a composite number because these are all the factors of 36, right? And apart from 1 and 36, you have 2 and 18, 3 and 12, 4 and 9, 6 and 6, right? And I wrote this to explain an important sort of like an important rule that we will use to improve the performance actually in our program. So let's say n is the number that we're checking, and let's just assume that it's a composite number. It's not a prime number, right? So and we can definitely uh, write n like this, right? So we can write this as a pair of factors, right? Like let's say 36 is the composite number. We can write it like we can say it is uh, it is the result of 1 times 36 or 2 times 18, so 3 times 12, whatever, right? So we can take this composite number and write in this form, right? And if we assume that this a is greater than the square root of n, right? And then we also assume that b is also greater than square root of n. Then when we multiply a and b together, then the result will be greater than n itself. So that's not possible. So we started with saying that like a times b is n. So then this assumption is definitely not right. So what that means is one of these numbers, a or b, is definitely less than square root of n. And that's the conjecture, that's the proof, right? So even like if we just take this example 36, so we can see that like the square root of 36 is 6, and we can look at each of these factor pairs, and we can say that like at least one number is less than square root of 36, which is 6, less than or equal to. So this is the only pair where both the numbers are equal to the square root of 36. So just summarizing this, so if we say that n is a composite number and n can be written in this form, like multiplication of two numbers and the factors of n basically, and if we assume that a is greater than the square root of n and b is also greater than square root of n, and then the multiplication or a times b will be greater than n itself. But we started with taking n and writing it in this form, so this cannot be correct. So at least one of these numbers you know is less than or equal to square root of n. So that's what this proves actually. So coming back to the solution, we we have a similar solution, but the main thing that's different is this guy. So instead of checking all the numbers, like starting from 2 through, if we are checking 97, like then we're checking up to 96, right? So in the first solution, we took numbers 2 through 96, and we checked each number. Like we took each number, and then we did 97 mod 2, 97 mod 3, 97 mod 4. And similarly here, instead of going up to 96, we're only going up to the square root of 97. I don't know what that is. So the square of 8 is 64, 9 is 81, 10 is 100, right? So we take square root of 97, which is 9 point something, and then we're casting it as an integer, right? A square root of 97 is 9 point something. So when you cast it as an integer, all the decimals go away. So that's 9 plus 1. So we're only going to have 3 to 10 in this range, and we have this other comma 2 in the range. What this means is we're starting at 3, and we're checking only the odd numbers, like 3, 5, 7, and 9. We're checking only 4 numbers, actually 3, 5, 7, and 9, right? Because we already before we get into this for loop, we already check whether the number is divisible by 2, and all the even numbers are divisible by 2. So we don't have to check even numbers again, and that would be basically wasting resources, right? So why would I check the even numbers again? Because all the even numbers are divisible by 2, right? So we eliminate a lot of iterations here. So we only do like 3, 5, 7, and 9, and then we check all those numbers, and then we say whether it's prime or not, right? So this time actually I am going to run both. I'm going to call both the functions, and I'm going to be checking the same number 97, right? So you can see that the first function actually, again, like as we saw before, it says 97 is prime, which is correct, but it took 95 iterations to get to that result. But then in the second solution, it took only 4 iterations to get to the same result, right? Then that's because of this main sort of like a thumb rule that not a thumb rule, sort of like this formula that we proved actually that we just took a look at. So we know that one of these numbers is going to be less than or equal to square root. So we might as well just check only till the square root of the number, right? So, and then we are again like eliminating all the even numbers, because uh, you know all the even numbers are divisible by 2, and we take care of that in one of the initial if statements, and there's no point checking the even numbers again. So, and you can see that the number of iterations have drastically reduced. So, let's say like each for loop takes a second on whichever computer or host it runs. And that's just for example, right? A for loop is probably not going to take a second. It's probably going to take microseconds or even nanoseconds. But let's just assume a for loop, just one iteration takes 1 second. So the first function would have taken 95 seconds, whereas the second function would have taken 4 seconds, right? So that's just is to show the second solution is much better. So what you want to remember for sure is, like, if you encounter this problem in your interview, just remember that you don't have to check uh, you don't have to take each number between 2 and whichever number you're checking, whether it's prime or not. Like 2 through that number minus 1. You don't have to take all the numbers and go through this for loop or iteration. You can only check you can only check till the square root of that number. And and also eliminate the even numbers, because if it's not an even number, so an even number always it has like 1 and that number, and also 2 has factor, right? So there, like, basically it fails the prime number rule, right? So just remember all these things, and you should be good. Okay. So, and also just do check out my other video where I talk about big O notation and uh, how to actually evaluate an algorithm and arrive at a big O notation. Yeah, all right. So if you like my videos, again, please subscribe and share it with your friends on your social media accounts. Thank you.